So this is the Servotube, which has sine cosine, 1 volt peak to peak for analog Hall, and feedback for commutation and interpolation. This is an Accelnet ADP drive, is an 800-21111, 2111. This is designed not only to output emulated incremental A naught, B naught, X naught, with respect to ground and shield. It also outputs Halls U, V, and W, digital Halls emulated from the sine cosine out of the 3 outputs. I do have a red blinking light right now because I forgot to hook up my motor. There's no sine cosine. Never do this. That's hot swapping. You should turn the power off and back on, but I just wanted to show you that when you disconnect your feedback, you get the red light. But when you move the motor, you get Halls, right? So this emulation, you don't really have to hook up the software to do anything. You can use the software, the CME software, for troubleshooting if you want. That's fine. We'll take a look at that. But really, there's just a pair of magnets in here. This is the size 25 motor, which has a pair of magnets that measure 51.2 millimeters. If you had the 38, that's 71.2 millimeters. If you have the 11 millimeter motor, the small one, that's 25.6 millimeters. And this thing will give you 4096 interpolation. So divide that by 4096 and you get the amount of resolution. The resolution is in microns, and then you probably are plus or minus a few counts. It's not accuracy, of course, because there's a stack of magnets and how accurate is the measurement of the magnet. But it is resolution. And so it's pretty good for a lot of applications. Yeah, so today we're just showing the emulator because somebody has a Allen Bradley Rockwell and they want to hook up the Servotube to the Rockwell, but Rockwell doesn't take sine cosine 1 volt peak to peak analog Hall. So we need an emulator. And so that's what the Copley drives. This is a low cost Accelnet with D sub connectors. You hook up 24 volts. I hooked it up to ground and HV because I want to see a green light. You could use aux, but you'll always have a red light. You could connect over the serial port with the Copley SER-USB-RJ11, and you can take a look with CME what's going on. Or you could get like these other Copley drives and talk from your Allen Bradley over the serial port. Or Copley has Ethernet now. We can do Modbus-TCP. And of course, we're still developing the Ethernet IP, but that will be available in a Xenus Compact. You know, a little bit more than this guy because it's got a power supply built in. And this is a Xenus 2 axis, so a little bit more again for the 2 axis. So one drive could do 2 motors. You could technically drive the motor from this drive, but then you'd have to like send serial commands or something. I don't know how Allen Bradley could talk to, maybe over the CAN port? No, maybe not. We don't like to do device net, so I guess just serial or step in direction. But this is a big motor. So this big motor here, you know, maybe you got 120 or 240, you want to go wicked fast, and you need, I don't know, 10 amps or something. We're just using the 3 amp continuous 9 amp peak drive, but some of the smaller motors can do good with that. So I'm going to show you the wiring diagram. This is from the app note for the 800-2111. We missed a number there. I'll get that fixed, but 2111. You got the Servotube here with your sine cosine and your +5 and ground, and you wire it through twisted pair shielded to the drive. And so that goes in on the feedback connector of the drive, J2. And of course you have power supply, 24 volts. I hooked it up to the HV on pin 5. This shows aux HV on pin 6, but I don't like my red light showing, so I'll hook it up to the pin 5 HV pin. And then coming out of the drive, of course, shields goes to pin 1 ground, and A naught, B naught, X naught, and then with respect to ground, U, V, and W, these would be twisted pairs typically. And then for motor temperature, you just snag that right from the motor and go right into the Allen Bradley. It's the green and the paired with the green-black wire for motor temperature, so you can shut down if you're going to burn up your motor. The other thing I wanted to note too is the metal case is anodized, so you got to make sure you scratch the surface to get to the plate. Now, if the case is not finding a good path to Earth, you get some noise. So make sure you got a good path for the case to Earth so that the connectors and the shields all find a good path to Earth. All shields must find a path to Earth. All cases must find a path to Earth. So let's take a look at the ADP, and we'll see the wiring diagram again for the motor. You got your U, V, and W. Well, that's if you had a motor with incremental halls, but this just has sine and cosine with +5 and ground and shield, so that's going in and then coming out. You got A naught, B naught, X naught, and then you got 3 outputs: halls U, V, and W, shield, pin 1, +5 and ground coming out. Take a peek at the Servotube here. Of course, we know this motor because it used to be a Copley motor. Here's the 25, just a diagram of the different configurations, and they're shown with a PLC and stepper direction or indexer analog command. Anyway, so there's Copley can control this motor too, and here's the 11 millimeter with a 25.6 pitch. So that's a good look at it. We're going to take a peek at what CME does. So I've got this 800 2111, which is nothing more than, you know, a 3 amp, 9 amp drive rated for 48, 75 volts, a 91 volt shutdown. Firmware, this is an ARM version, so it takes a sine cosine, so no extra money. We pay the encoder fee for this drive. No more -S for sine cosine. We're using the ARM firmware 2.00, so that's the latest firmware. The techie stuff here is all we had to do really is, you know, for the phasing, we set -180 for the Hall offset, and then, you know, you can simulate the motor motion here. To get the halls to come out, we use the ASCII command line. So we'll take a look at that. Tools, ASCII command line. I'm going to get from RAM 0x70. So that's the output 1. And then 71 is output 2. And 72 is output 3. 72. And you can see this value 8. Everybody is 120 degrees apart starting at 30. I don't know why 30. You could start at 0. So you'd go 0, 120, 240. But to emulate the old emulator, or emulating the, used to do it with an ACJ-S, which nobody bought because Dunker came out with their own emulator. And now Dunker made their emulator obsolete. So people are calling us again. Hey, we need an emulator. Got to hook up to this Allen Bradley. No problem. So we're doing it with an 800 2111. Just to show you some little tricks here, we've got the control panel, so we can monitor a little bit of, you know, you can watch the phase angle as you go through a pair of magnets, you know, and the distance is relative based on the counts. Like I said, this is a 51.2 millimeter. You don't need to change this. It doesn't, the emulator doesn't care which motor you have, unless you're reading it something over the serial port. But you can see, you can enter this value if you want. Maybe I have a 71.2 millimeter motor. I could put that in there and 4096, and I'd get my resolution. It's 12.5 microns of resolution, not accuracy, because the plus or minus account and the magnets are stacked. So, you know, don't sell it as extremely accurate Renishaw feedback, right? That's something completely different, but it's fine enough for most applications. We can also look at the, here I just moved it by hand. I started at 0 and I triggered a rising edge from 0 counts. I just moved it by hand, a distance. I've got Hall states out 1, 2, 3, UVW. I see my sine and cosine coming in, and I see my counts, right? So this is just counts, whatever the magnetic pitch is, divided by 4096, and that's your count resolution. I could clear the fault here using CME or cycle the power because I like to see, you know, on the drive, I like to see a green light. So green light's a happy light. Turn the power on, everything works just fine. Move the motor, get your counts, and of course you can use CME to set up and trigger this. So what I did is I moved the motor down here to some position that was near 0. You know, maybe I could set that to 0, go a little further. So what I did to trigger it was as I moved through 0 on channel 1 position. So let's clear that, hit record. So there's a move. I'm just moving it for like a second, and I'm gathering some data. You should see a nice sine, cosine, plus or minus 500 millivolts peak to peak. That's 1 volt peak to peak, plus 500 millivolts, minus 500 millivolts. Here's a sine and a cosine. They're 90 degrees apart, which gives us perfect Halls for commutation coming out of the drive. I presume, you know, if you have incremental encoder with Halls, you can phase the Allen Bradley. I haven't done that myself, but should be pretty straightforward.